Good. So now today I'm going to be going through some of the things we've done using the Collaborate class, using the Collaborate Blackboard Collaborate. So what I'm going to do now is to go through some of the thing we've done, then also go through some calculation with you. And if you have any question, all you need to do is just to raise up your hand. You can see I've raised up my hand now. So if I see this, I've raised up my hand now in two places because I log in using my laptop. I also log in using the desktop. So if I see this, I know somebody is having issues. Maybe you want to ask question. So once your question has been answered, you can drop your hand by clicking on the icon again. So that will go. I hope you understand that. So you can always just type yes. So if because I will keep asking questions during the course of the presentation. So if you understand, all I need to do, maybe you can just type in yes, or you can just click on the icon. You can click on the smiley face. So just to show that you are there. So that's why, so that I can know that you are there. Trisha is having issues. Trisha is having issues. Trisha is coming in and off. I think the problem might be from your hand, Trisha. Maybe the network, internet connection from your hand. Is Tom there?
Yeah, I'm here.
Good. Now, let's just go to the lecture. It's going to be recorded so people so I can have time to go over it again. So I'm going to go through the revisions, just like I said. Now, the whole essence of this is just to go through the overall learning outcomes of the modules, and we all understand that at the end of the module, particularly in your exam next week, you will be required to demonstrate that you have the scientific principles which influence the quality of raw materials. And again, you should be able to compare and contrast subjective and objective methods of raw material assessment. And the learning outcome number 3 is the use of analytical methods to assess the physical properties and contaminants of food. Now, this includes the use of some of the experiments you did when you were here during your study week, the fish experiment. You remember you did some Torrey scale and things like that. You'll be able to demonstrate your understanding of all that, and again, calibration curve and so on and so forth. And in the learning outcome number 4, you should be use of advanced analytical laboratory methods to assess the composition of food products. So there's so many things you need to demonstrate in here. So I'm going to be going through some of them not necessarily in that order, but in the order of our delivery during the course of the module during the semester. So you remember when we started, the first thing we did was to introduce the module to you, and the second the first one that we had on week 1 is the concept of food quality assurance. Then week 2 and week 3 we did something on quality of raw food materials. Then in week 4 we did subjective and objective methods of raw material assessment. Remember our Apple lab experiment. So this was covered under this session. Then we also talk about the compositional analysis of food. Then we discussed in week 6 the instrumental, where I put in a lecture delivered by Professor Tony Taylor during the study week. That was in week 6. Then in week 7 we have our study week where we had the 4 practicals and some lectures. Then in week 8 and 9, that was when you were asked to do your practical reports. Then and again in week 10, you are also your last 2 practical reports. Then in week 11 we have the advanced method in food commodity analysis, where we did some calculation using calibration curve for HPLC. Now, so week 1, what did we do? The concept of food quality assurance. Now here you are expected to understand what is food quality. You should be able to define food quality, and as you can see, food quality is defined as a composite of characteristics which affect the ability of food to satisfy its definite requirements and determine its fitness for consumption. Now you can see there the word fitness for consumption. Now food quality is meeting the requirement for safe food. If you are telling me that this food is safe, this food is a quality food, you are telling me that that food is safe and it is fit for consumption. And again, you can also say that it is the extent to which all the established requirements relating to the characteristics of food are met. Now, there are so many requirements. We have legislation requirements, we have consumer requirements, we have so many requirements about food that we consume. So we want to be sure that all these requirements are met before we can say that the food is a quality food. And then we know that in terms of characteristics, we talk about appearance. That's talking about size of the food. Now we're talking about if you are telling me that the food is a quality food, it must come in the right size. For example, if you want to prepare your meat, if it is too big, you may not be able to have a proper cooking at the center of the meat. So you want to make sure that everything is in the right shape, is in the right size. Now and again, color is also very important. Consumer, we are attracted by what we see. Now the color is very important. If the meat is supposed to be red and it's not, you want to say no, this is not good for me. Now if the color is not the right color, there's a problem somewhere. Then the shape is also very important. And again, the flavor, it has to be appropriate. It has to be the right flavor, the right texture, and again, most importantly, the shelf life. Now, if you're talking about the food is a quality food, you want to be sure that the shelf life is appropriate. It's within the life on the food is still there before you can say, okay, this food you can consume it. You can say the food is safe, because if the shelf life is no longer, for example, if the food is meant to expire maybe next week, now you can't tell me that food is a quality food in the next 1 month, because you expect microorganisms to have grown, multiply, and so the food is not fit for consumption. The aroma is also very important, the viscosity, and again the packaging, because packaging protects the food, it prevents contamination, so it has to be right. Then it has to be all these put together makes the food safe, and as a result of that, we can say the food is a quality one. And again, labeling is also very important. Because some people will react to some food. We have about 14 allergens. So if I'm going to eat egg and that egg will cause me a problem, that food is not safe for me. So if I'm going to eat a crustacean and it's going to cause me a problem, that food is not safe for me. So you need to make sure that the labeling is done properly, so that people can know what they are eating. If it is not good for them, it is not safe for them, so they don't buy it. Now, we know that there's 3 components of food quality. We have the sensory, we have the convenience and technical quality, and we also have the nutritive value. Now, the sensory is talking about the texture. The sensory is talking about everything that we've described. I'm going to go back now. The sensory is talking about. Let me see if I can use this. The sensory is talking about the texture. It's talking about the flavor, the aroma, and so these are what the sensory is talking about. It's talking about the flavor and the texture. Then, if you're talking about the nutritive value, it's talking about the content. It's talking about the nutrients, the protein, the carbohydrates that you have in the food. Now, you're going to indicate all this by your labeling. So, talking about the nutritive value, and again, the convenience and the technology quality. This is talking about the packaging, the size. Now, you want to make sure that you can take the food from one point to the other. So, these are the things you need to consider when you're talking about food quality. Now, why is it important? Now, it's important because you want to make sure that the food is fit for consumption. Consumers are asking for it because you need to remember that they need to be satisfied before they can buy your food, and so on and so forth. Then there are also the concept of product specification, then meeting customer requirements, so as safety requirement, nutritional requirement, and sensory requirement. And again, there are legal requirements also. There are legal requirements that you need to put into consideration. Now, you need to meet those rules and regulations. Just like last year, December, we have EU regulation on. We have some changes with regards to labeling. So, in terms of allergen requirements and labeling regarding allergen and so on and so forth, these are the things we need to put in. These are the things that are very, very important related with respect to food quality. Now, in week 2, we talk about the quality of raw material. We talk about meat. We talk about milk. We talk about fruit and vegetables, and then the fish. This was covered during the study week. You remember Tony Taylor talking about fish, talking about tourist scales, and so on and so forth. These are very, very important. Now, under the meat session, we talk about, we mentioned that there are 2 major aspects of meat qualities. We have the nutritional or compositional quality, and we also have the sensory or eating quality as perceived by consumer. Now, the technological aspect is also there, but we want to focus on the 2 major aspects of meat quality, talking about the nutritional composition and then the nutritional quality and the sensory quality. Now, the nutritional quality is talking about the protein level, the fat content, the vitamin. Now, the sensory is talking about the palatability, such as visual appearance, smell, firmness, juiciness, and tenderness and flavor. These are also very, very important when you're talking about meat quality. And we also I gave you these figures talking about the meat quality factors. Now we have seasonal, and all of these play crucial roles in the assessment of meat quality by consumer. The tenderness is very important to the consumer. The color is very important. The water holding capacity is very important for the consumer. The juiciness, the surface texture of the lean is also very important, and the flavor is also very important to the consumer. Now, yeah, I also remember talking about the colors of meat. You know, we have the purple color, we have the bright red, we have the brown. Now, the question now is, which one do you think is the best? But the truth of the matter is, meat can be in these 3 different colors, depending on the oxidation state of the meat. Now, in the first state, where we have the myoglobin, which is purple red. Now here, the oxygen level is different from the oxygen level that you have here. Here we have myoglobin with the bright red. Here we have oxygenated meat. We have meat. Here we have oxygen has been. Let me just show you the next. Now in this phase, myoglobin is in the reduced form. In the first one, is in the reduced form. Now, this is the reducing condition naturally occur in meat. Now here we have purple or purplish red. Now, when it is bright red, this is what we have when the meat is fresh. Fresh meat. This is the fresh meat color, and it's the most desirable color for fresh meat. Now, for people, this is what they prefer, because then they believe that's the sign of freshness. Now here, this is not really good. People will not want to go near this meat. The brown myoglobin color. Now when the iron ring in the meat oxidizes from ferrous to ferric, the pigment turns brown. Now what happens here is the oxidation of ferrous in the meat to ferric. Now the question I want to ask is, now if you are a consumer, and then you are talking about buying fresh meat. Now what you would like to see is you want to see it bright red. But when you want to preserve your meat, and if you vacuum pack your meat, so oxygen is absent. Now if oxygen is not there, It can't be bright red again. If vacuum vacuum pack meat cannot be bright red because oxygen is not there. It is that oxygen that is giving that bright that color. Now, so you will discover that in the next I'm going to show you here in this slide. You can see that in the ozimyoglobin you can see oxygen coming playing an important role here. Okay, you want to ask question, Tom?
Yeah, I'm just wondering what level of detail do we need to know about this process? So, do we need to know the full understanding of oxygenation and the deoxygenation between all the different myoglobin factors, or do we just need to know what the difference is between them?
Now, I think that's a very good question. I think it's important. You don't need to cram them or I think what you need to know is how does it apply to you? I'm going to go there now. How does it apply in terms of processing and preservation of meat? How does it apply? The application of all this. Now, that's what I think you need to know. For example, if you go to the next slide now this is talking about myoglobin. Now, this is what you're going to see immediately after cutting meat. Now, if you understand all these basic principles, you'll be able to look into how this applies to you. Now, I'm going to explain something to you. Now, if you cut meat, now you have the color is dark. You have the meat color is purplish red. Now, myoglobin can change from dark purple color to a bright red color. Now, it can change to bright red color because of oxygen coming out from the air. Now, the oxygen coming out from the air will do we facilitate the change in color. Now the second one is ozimyoglobin. As oxygen from the air comes into full contact with the exposed meat surfaces, it is absorbed and bound to the iron. Now, what happens is this: the change from purple myoglobin color of the fresh cut meat to the oxygenated bright red color of the ozimyoglobin is known as bloom. Now, that's the change in color. Now, if you look at the next slide, that's talking about methylmyoglobin. Now, the myoglobin and ozimyoglobin have the capacity to undergo oxidation. Now, oxidation is referred to as electron loss, which turn the pigment to a brown color and yield methylmyoglobin. Now, the pigments, we have the three pigments: the myoglobin, the ozimyoglobin, and methylmyoglobin can be changed from one to the other depending on the condition at which the meat is stored. Now, you can change the pigment, but immediately after you've cooked your meat, you can't change the pigment again. You are going to denature the protein. So, and methylmyoglobin is going to be formed, which cannot be changed to another form of pigment. Now, why are all these statements? Now, we look at a paper about meat color, quality, and packaging. Now, the meat color and packaging, we have two types of storage method. We can have modified atmosphere, where you have your oxygen as one of the mixtures of gases. Now, if in your modified atmosphere you want to have 80% of oxygen and 20% of CO2, what happens? Now, going back to what I said earlier, now because you have 80% of oxygen gives the meat a stable, beautiful, bright red color. This is what the consumer wants to see. This is what they want to see. Now, this stable, bright red color, if you go back to the previous slide, is being referred to as the ozimyoglobin. Now, that is what they want to see, because when you cut the meat, immediately when you cut the meat, this is what you're going to see. You're going to see the purple color. But immediately after some seconds, oxygen from the atmosphere will react and to the bright red. This is what people will see, because it changes very fast. So they will see this. Now they will see the ozimyoglobin. Oxygen has been added to it. Now, if you see this, you will say, okay, this is a fresh meat. So when meat is stored in this modified atmospheric condition at 80% oxygen, it's going to be looking very fresh, no matter how long, because oxygen is going to be there reacting to it, making the color to be bright red, and then oxygen will give the meat a stable color, beautiful, bright red color. And most consumers take bright red color as a sign of what? Freshness and meat of good quality. Hence, food chains choose this particular gas measure. Addition of CO2. Now again, because we have 20% CO2, CO2 is going to inhibit the growth of bacteria. So this is another advantage. So hold on, please. Do you want me to connect you, or you want to use my laptop? No, not at all. So if they need you, I will connect. Yeah. Good. Yeah. Good. Good. Thank you. So I've just spoken with Tony, and he said that if you have any question for him, so he's more than happy to answer your question. But he's still very busy now, but he will be joining us when you have your question. So you can see CO2 will also inhibit the growth of bacteria. Meat has longer shelf life than if it has been packaged in a tray wrapped in plastic wraps. Now that's let's look at the disadvantage. Now the disadvantage here is that oxygen stops tenderization and the meat can be tough. That's the problem. Yes, you can see the bright color, but in terms of the eating quality has been affected. Now the tenderization can be stopped, and then what happens at the end of the day is that it's going to affect the texture of the meat. So the meat can be tough, and high oxygen content makes the meat easier to oxidize. Now again, you can see because you have high oxygen content, you can easily oxidize protein, you can easily oxidize fat. Now you know oxidation of fat. You know what that means? Rancidity. Now if you oxidize protein, you're going to be getting a tougher meat. Now because of oxygen, vitamin E content will be reduced. Then high oxygen content will oxidize fat, like I said earlier, and that makes the meat to taste rancid. Now the bright red color of MAP beans in high oxygen content makes the meat look like pre-cooked at a lower temperature. Now the problem with this is when your meat is appearing cooked at a very low temperature, the danger is the survival of microorganisms. Now we are meant to cook our meat according to legislation at about 70-something plus degrees Celsius, and if the meat. Okay, yeah, I'm listening to your question.
Yeah, just a quick one, Moses. The second to last point there, what does it mean the meat looks cooked at about 55? Why would the bright red colour do that? That's one of them. The second question would be what within the MAP packaging prevents it from going one stage further to the myoglobin stage?
So, can you come again, question one, please?
Yeah, question one was just around the second to last point, the MAP beef and IO2. Yeah, this one. Why does it look cooked at about 55 instead of 70?
Now the reason why it looks cooked is because it's bright red. Now there's this deception. It can bring about deception. It looks as if it has been cooked. That's what is going to happen. It looks as if it has been cooked at a very low temperature, whereas it is not done. And by the time you look at it, some people, when they look at the texture, because at home we do not have thermometer to measure the temperature. All we look is the appearance. We look at the appearance, and that appearance can be very deceptive because it's a bright red meat in a MAP packaging, and once we have it in the hot water or warm water, it changes quickly, appearing, looking as if it is done, whereas it is not.
Right, okay.
So it's because we don't have the thermometer. If we have the thermometer will tell us no, it is not there.
Yeah, so it's more perception of a customer because of the brighter colour of the meat originally, so they think, oh right, that's cooked quickly, and this is where you get the issue from. Right.
Yep. Yeah, and the second question, please.
Yeah, the second question is just looking into the MAP packaging. What prevents the meat from going to the third stage through to the myoglobin stage?
Now, what is preventing that is the oxygen content. Oxygen content will make, because you have created an environment for the meat.
Yeah.
You have an environment there. The oxygen is there. The oxygen there will will prevent that from happening. If you look at the previous slide that I showed to you here, because you have oxygen in that atmosphere and you are not losing that oxygen, it's there, it's intact. So it's going to be in this state. It's going to be bright red. You have that oxygen. That's what is doing that. That's what is doing it. If you look at the map gas nature, it's 80% oxygen and 20% CO2. This is what is doing that. This is what is preventing that. Okay?
Yep.
Do you understand that now?
Yeah, thanks.
Good. And the second one is vacuum pack. Now, talking about what people have done, vacuum pack seems to be the best, but unfortunately the meat color looks purple because no oxygen. So when it looks when you are seeing the purple color, you be, oh no, this meat is not fresh. It's not. I can't see bright red. Now, but in natural sense, we have tender meat than mark meat, and again, it tastes better than beef packed in gas nature with much oxygen. Now, the taste is better. The tenderness is good. Is very good. Now, again, because it's a vacuum pack, meat loses less liquid. Now, liquid because you do not have oxygen doing some because the presence of oxygen will definitely be doing some will be initiating some reactions. Because oxygen is not there, you have a longer shelf life when compared with map meat. Because no rancidity, no fat, no change. There's no change in protein as a result of oxygen reaction. There's no change in the fat content as a result of oxygen reaction. So you have a longer shelf life. And like I said in the last one, any form of undesirable oxidation reaction are eliminated. But the advantage is this: no stable, beautiful, bright red color. That is what the consumer wants to see. May not appear fresh to most consumers. Less attractive to most consumers. A bright red color appears to be a sign of freshness and good quality. This is what the consumer wants to see. But unfortunately, they won't be able to see that when the meat is vacuum packed. Do you understand that? Good. I can see you're nodding. Now, then we also talk about the water holding capacity, and we talk about 4 different methods by which water in meat can change. You have evaporative losses, drip losses, cooking losses. Now again, water can also be gained by addition of water during the processing. Now, talking about meat, we have we talk about the meat composition, meat testing and quality and control. Then we talk about the alkaline phosphatase test. Now, talking about the factor affecting meat composition, the breed of the animal, the genetic background of the animal, the stage of lactation, then the nutritional quality of the animal's feed, the frequency of making age, the incidence of any disease such as mastitis, then the general environmental conditions, season and weather. So these are the things that will affect the composition of meat. Then we also talk about the meat quality control. You know, meat is highly perishable. It's a perishable commodity and spoiled very easily. And the reason for that is because of the high nutrient content, which make it the perfect breeding ground for bacteria. Now, meat, as we have it from every other, contains very few bacteria. So meat coming from the animal has very few bacteria. And the natural inhibitory systems in meat prevents significant rise in can for the first 3 or 4 hours at ambient temperature. Now, but if you can do this, you can do the cooling to 4 degrees Celsius within the first 3 to 4 hours. You are going to maintain the original quality of meat, and this is very important to ensure good quality meat for any further processing or consumption. Now, the first 3 hours, because within the system, within the commodity, within the meat itself, we have an inhibitory system that prevents rise in microbiological counts in the first 3 to 4 hours at ambient temperature. But this has to be done as quickly as possible, because ambient temperature for meat is a danger zone. You need to get it quickly down to 4 degrees Celsius as fast as within the first 3 to 4 hours. So these are talking about the meat quality control. Then, and there are also testing techniques. Now, we can test meat for quantity. We can do this by measuring the volume or weight. Then organoleptic characteristics in terms of appearance, visual observation, taste, and smell. Then the compositional characteristics, especially fat, solid content, and protein content. Then physical and chemical properties, these are also very important. Then hygienic characteristics in terms of hygienic condition, cleanliness, and quality, the environment where we are producing it. Then again, because the adulteration with water, we can also test for if water has been added or preservatives or added soil, we can test for all this. Now, talking about different tests that we have density meter. Now, this one will help us to measure the density of milk. Now, if water has been added, we know it's going to be less dense. So this will reveal that. Acidity testing to measure the lactic acid in milk. Now, acidity, now because we are meant to have in a fresh when milk is fresh, we have lactose. When immediately the lactose is being converted to lactic acid, it's no longer fresh. So that can help to determine the level of freshness. Now, acidity, when you test for lactic acid in milk, and you are saying, oh, this is, I can see significant amount of lactic acid in this milk. So you know it has been there for a very long period of time. And then GABA test to measure the amount of fat in the milk. Now, cloth on boiling test to determine whether the milk is sour or not. Now, when what makes it sour is the presence of lactic acid. So we can also use it to determine freshness. Now to determine let me look at something. I think let me see if I can see this. Now, if you look at the when milk gets older, what happens is that bacteria will grow in it, and this bacteria they undergo respiration. They use the oxygen and lactose in the milk and turning it to CO2 and lactic acid. So when you use cloth on boiling, now that relates to lactic acid. Or if you use bacterial analysis, that relates to growth or multiplication due to factor of time. Now, if you leave it for some time, now that will reveal that okay, this is not fresh again, because you can determine the amount of microorganisms that you have there. Cloth on the boiling will also reveal that we have lactic acid in this milk, so it has been left there for a long period of time. So these are the things that you can use to determine whether the milk is fresh or not, depending on how you explain it. Now, bacterial activity, like I said, you want to be sure when have you harvested this milk, for how long has it been kept here, and so on and so forth. You want to determine the freshness, the shelf life of the milk. And you can use resazorin dyes or methylene blues to do this, to check for microbial quality of milk. Then somatic cell amasticity, this is just to be sure that the cow is healthy, the animals is healthy. Like mastitis, when you have the inflammation of the mammary gland and other tissues, you want to be sure that the milk you are using for food for consumption is coming from healthy animals. Now, it counts under 200,000 somatic cells per milliliter in bulk herbs milk indicates an absence of mastitis. If it is above 500,000 per milliliter, indicates a higher incidence of mastitis in the herbs. So we need to do something about that. You need to attack it from the source, and these are the tests that you can actually use to determine where is the problem coming from, and you can do the appropriate actions. You can implement the appropriate action rather. So alkaline phosphatic test is because when you harvest your milk, when you pasteurize your milk, We want to be sure that that pasteurization is effective. Now, if because alkaline phosphatase is a heat sensitive enzyme, so if you do your pasteurization completely effectively, you should inactivate alkaline phosphatase enzyme. So if it is not inactivated, you know there's a problem. So if the pasteurization is not effective, you know that milk is not fit for consumption. This will help you to know that your pasteurization process has been effective, and if it is not, you need to do something about that milk. Discard it and look at the procedure for your test. Now we talk about fruits. We talk about factors affecting fruit quality. Okay, questions? Yes?
Sorry, it's a real quick one, Moses. With the milk quality and testing area, do we need to know anything about the antibiotic testing or anything such as that on the passports into the milk?
No, I can't hear the question.
I'll type it.
No, I don't think we cover anything on this bit. And no, we didn't cover anything on antibiotic test for milk intake. I don't think we cover any. Do you understand that? Good. So, then factor affecting fruit quality. Now we identify three groups of factors. We talk about nutritional factors during growth, factors associated with time of harvest, factors associated with storage. Now, we talk about fruit maturity, we talk about organoleptic and metabolic changes that occur during ripening. So, one thing I want us to know is that fruit is a living tissue. And if fruit is a living tissue, what happens is that it takes up oxygen and it gives out CO2. Now, therefore, it generates heat energy in itself. If you tell me, this apple is, I think that this fruit that I have there is 20 degrees Celsius, and it's going. It's 5 degrees Celsius, and it has to be there. I don't believe that because because with time the energy is going to be generated because of the metabolic reactions. Now, once energy is generated, it is going to be generated, and once that happens, temperature will rise. And if you want to keep the temperature down, you need to store the fruit in an appropriate environment. So I think I asked a particular question about which one do you think is appropriate for fruit storage? Control atmosphere or modify atmosphere packaging, MAP packaging. No, MAP packaging is static. Once you've modified the environment, it's going to be static and you're not changing any gas. But in an environment where the store fruit is taking up oxygen and is giving out CO2, that environment is going to change. So you actually need a dynamic environment to store your fruits. You need a controlled atmosphere, an atmosphere that will measure what is the percentage of oxygen in the atmosphere. You need a system that will measure what is the percentage of oxygen in this atmosphere, what's the percentage of CO2, and it gets appropriately. Like, okay, we need more oxygen now because it's like the oxygen in the atmosphere has been used up by the stored fruits. It's like we have more CO2. Okay, I think we need to take away CO2 from this atmosphere. You need a dynamic atmosphere to actually store your fruit. And again, the heat that is being generated, depending on the amount of heat energy generated, you need a system that will respond appropriately, take out the heat from the environment you have stored your food. Otherwise, there will be a problem. So you need a dynamic environment to actually store your your fruit, because your fruit is a living tissue. Now, talking about subjective and objective method of raw material assessment, that led us to our study week on fruit on apple texture analysis. Now, we talk about fruit texture, we talk about subjective method of raw material assessment, objective method. We talk about the skin strength, flesh, firmness of apples using the texture analyzer. We did a lot of this during the study week. And then we talk about we define food texture as a manifestation of the rheological property of a food. And it's important because it affects food processing and handling. Now, your texture will affect how we process our food, how we handle our food. It influences our food habits, affects shelf life, affects consumer acceptance of food. If your biscuit is very soft, consumer will reject that. So these are things that we look into: process control, quality control. Texture is very important for all of this. And then we talk about the subjective method, where you have the sensory analysis, and then we talk about the objective method, that which we did during our practical week, instrumental method of analysis. Then sensory analysis, you remember, it includes the use of our 5 senses: smell, taste, sound, and touch. Then evaluation of food texture by touching. Now you can also have the tongue, palate, taste in the mouth. And because because this is a subjective method, no individual opinions count. And again, this is not, we have variability from the assessors, although this can be reduced by training the assessors. Now the instrumental method is just to measure the property of food by replacing human sensory evaluation as a tool to evaluate, by using machines, to replace the human sensory evaluation. We want to use mechanical tests to replace the human sensory evaluation, and as a result of this, experimental variability is minimized. Now we can change ingredients in our food. We can do this. We are able to do this because machines can actually help us to do the measurement very fast. An objective testing also uses equipment. Now, instead of human sensory organs, we can use the machine to test the food for us, test the texture, and we can test so many things. And again, the instrumental method of analysis will also involve checking for protein content, checking for fat content, which is very, very possible using some machines, using some advanced machine at this because due to recent advances in food processing methods. And again, in week 5, we talk about compositional analysis of food. Here we talk about importance of food analysis. We talk about moisture. Now here I'm going to be talking about moisture, total solid, ash and mineral analysis. Now I won't want us to forget the crude lipids oil analysis, crude fat analysis, protein analysis is very important, carbohydrate analysis is also very important. Because of our times, I will just talk briefly about this three. But before I go on the issue of fat analysis, you remember I uploaded additional material that talks about rancidities, the types of rancidity, and how can you prevent it, and so on and so on. That's also very important. Now let's go quickly to food analysis. Now, just talking about what we are talking about, emphasizing on what we have been discussing on food analysis. Why is it necessary? Government regulations. Now, labeling now requires the percentage of fat, sugar, salt, and moisture in many products. Now, labeling, very important. Quality control to monitor consistency is very, very important. New product development and product innovation. We need food analysis to do all this. And don't forget, we call components of food, we often call them nutrients, and we have carbohydrates, protein, fat and oil, vitamins, minerals, and waters. These are the 6 main components of foods, and we have means to analyze each of them. Now I'll quickly go to the first one, which is total solid analysis. Now we are talking about moisture, and are you raising up your hand? You want to ask a question? Okay. Now, moisture and total solid analysis. Now, why is it important? You remember that moisture is a quality factor in the preservation of food and affects food stability. Now, when you're talking about shelf life of food, moisture is very important. Now, we are talking about transporting food from one point to the other. moisture is very important. If you reduce, for example, we have a concentrated milk, we have a powdered milk. Now, because we remove the water content, it's easy for us to take them from one point to the other. Now, also in compositional standards, moisture and solid content are very, very important. So moisture, very, very important. And this is the formula we use to calculate percentage moisture, which is very straightforward. Percentage moisture, weight by weight of water in the sample, weight of the waste sample. Oh, good. Question? Yeah.
Hi, sorry, just turning the microphone back on. Also, I mean, these are quite simple calculations, but are we expected to do some of these and remember the formula?
Yeah, yes, yeah. There are some calculations you'll be required to do because we are talking about food analysis. So there are some calculations, and at the end of this, towards the end of this presentation, I will be showing you some example. And if you have any question in particular, you can ask me.
No, that's fine. It's just so we're expected to remember and know all these different for moisture, the weight on weight, and the samples and the dry samples. We're expected to know that then.
Yes, yes.
Thank you.
Yep. And then another thing is the choice of moisture analysis. This is very important for people working in the industry. If you want to analyze moisture content, what methods are you going to use? Now, what methods? This is very important for people working in the food industry. Now, you want to be sure that if you want to analyze the moisture in your food, how do you determine the appropriate method? The first thing you need to think about is the expected moisture content. Now, if the moisture content is very low, there are so many methods out there, approved methods out there. Now, but how do you know which one is appropriate? Now, some methods can determine as low as 0.000%, 0.0001% of water of moisture content in food. Some cannot do that. So you need to know amount of moisture content you are expecting in your food. Now, the nature of other food content. For example, if you have some content in the food, some constituents in the food that are heat sensitive, highly volatile components. Now, by the time you heat them for a very long period of time, you get rid of them, and you'll be thinking you're getting rid of the moisture. No, it's not. You need to look at that. If you think that this moisture, this food I'm analyzing contains some volatile compounds, you need to use methods that will not require heat too much. There are some methods that will not require heat to analyze your moisture. Now, again, equipment available. What do you think you have in place that can analyze the moisture content? Then the speed requirement. Now, how do you require this? Because speed is very important in the food industry. You want to get your product out there into the market as soon as possible. So speed is very, very important. You don't want your competitor to beat you. You want to get to the market ahead of your competitors. So speed, very, very important. Or maybe there is an audit, Tesco is visiting or Sainsbury's is visiting, and they're asking for moisture content. They need it as soon as possible. Speed is very, very important. Accuracy and precision requirement. For example, if the report you're going to submit to Tesco to Food Standard Agency for investigation has to be accurate because of the legal implication of submitting wrong report. So you need to look at the accuracy, the precision requirement. The intended purpose, just like I said earlier, regulatory or in-process plant quality control. These are factors that will determine your choice of moisture analysis methods. Now, another thing that is very important is water activity. Now there's a difference between water activity and moisture content. Water activity is actually measuring the amount of water that is available for microbial activities. Now, because you can say, oh, this food is very high in moisture, but what amount of that water that is available for microbial growth? That is very crucial. You may have a particular food, high moisture content, but with a very long shelf life. The reason is water activity is very low. There is low water activity to support microbial growth. So you need to look into that also. Microbial water activity, moisture content, there are different things, but And again, you also have water appearing in different form. When your water is not free, if it's in bound form, you have three forms of water. You have water of crystallization, we have free water, and when your water is free, so it's going to be part of the moisture content. But and your bound water is also going to be part of the moisture content. But in natural sense, the bound water is not available for microbial use. It is the free water. So if your water is bound to the food, not making itself available for microbial growth, so you need to look. You're going to be seeing some variation in the water moisture content in some food, and some food getting spoiled quickly, and while other with high moisture content is not getting spoiled quickly, just because the amount of water available for microbial growth differs. So that is why we tend to use water activities to determine how our food is going to support microbial growth, enzyme or vitamin decomposition. So why? I think I've explained all this. Why water activity, moisture content in food is not a reliable indicator of food stability. Different food with the same moisture content differ in their perishability. Yes, different food, but they have the same moisture content. The same moisture content, but they differ in their perishability simply because amount of water available to support microbial growth differs, although the moisture content is the same. Now, water activity is a measure of actual water available for microbial activities and other reaction in food. Water tightly associated with food constituent will be less available for microbial growth and other chemical reaction leading to food decomposition. I've already explained all this. Now, the second one is ash and minerals analysis. Now, this is very important for proximate analysis also. Now, we have inorganic residues remaining after ignition or complete oxidation of organic matter in a foodstuff. Now, there are two methods. We have the dry ashing and the wet ashing. Now, it's important that you also go through the calculation. We have some calculation in the lecture notes. Please go through the calculation, so they are very important. And the next one is week 6. Remember, you did this during the study week. Professor Tony Taylor covered UV and visible spectroscopy for you during the study week. The same lecture material that you have on your blackboard. If you have any question, we'll be more than happy to answer you. And in week 7, I covered this partly during the study week, and I'm going to continue because I promised to cover the second part, which is very important. Okay, yes, I'm listening to your question.
I just need to nip away for a couple of seconds. We'll be back in a minute.
Is it? Yeah. Okay, you okay, good. So now, can you hear me?
Your audio's off.
Okay, good. I think it's back now.
Yeah, it's back on.
Yeah. So now, week 7. So we talk about the quantitative analysis, talking about the calibration techniques. Now, you remember in your practical experiment, you remember you did some calibration curve. You have some samples with different level of concentration, and then the concentration you have actually determines the area you obtain from the chromatograms, and then you plot that. You have a curve. And you remember we actually using Bayes law. Now the measure of absorbance for a sample is also proportional. Now you remember the first one is the value of peak area generated by a sample in a chromatogram is proportional to concentration of the sample, and the absorbance for a sample is also proportional to the this is Lambert law. This is Bayes law, I think. And then the measure absorbance for a sample is also proportional to the concentration of sample. Now, what is that saying is that the absorber you measure here, whatever you measure from machine, this is talking about the chromatogram. Then you remember you did experiment on I'm trying to. I want to remember this experiment on the on make. Yes, yeah. You did an experiment on make, which talks about absorbance. Absorbance. So, for example, that absorbance is going to be proportional to the concentration of the sample, and your HPLC. Remember, you did something on Chrome. You have some graph coming out of the machine showing the peak, showing the chromatograms.
Yeah, it's high energy drinks.
Yes, yes. So there you have whatever you have in the sample is going to be proportional to the peak, to whatever you obtain. So putting all this together, you have your calibration curve, and then now this is the calibration curve. Now, something you need to put into consideration in your calibration curve is that your concentration is always at the x-axis, and the response, whatever you measure, the response you measure is the area. For example, the area of your chromatograms is on the horizontal, sorry, is on the vertical axis. And something I think I need to let you know is this. Now, if you are using your calibration curve, please, there's no room for extrapolation. For example, if my calibration curve is between 1 and 10 in the area side, I cannot be using, for example, when you remember your experiment, when you were trying to do the make experiment, your dilution was not to the if your dilution was outside the scale. I think one of the experiments you did, your dilution was outside the scale, so you are unable to use that, because you need whatever you're going to use has to be within the readings you've obtained. And again, I think in your experiment for the high energy drinks, your dilution was not, just some of the dilution you did was outside the scale. So if it's outside the scale, for example, it is just like saying I have the capacity of between 1 and 10. You can't come and say you want to use me to measure 100. For example, if a pump is designed to inflate a pressure of 1 to 10, and you want to inflate something 100, you need something for 100 psi. You can't use that pump for that. It's not going to work. So you need to, if you want to use something for 100 psi, you need to get something that is higher than that. So your calibration curve is very, very important. You need to understand that principle, that whatever you are going to use your calibration curve to do. So if you have your standard, you've generated your calibration curve, then you have your company sample that you want to know how much you have there. You need to do appropriate dilution. Sometimes you need to do trial and errors. You do trial and error. For example, in the past question given to you, you have some readings. Trial and errors. Which of them do you think is the appropriate, is the best? So you now say, okay, based on this dilution, I think this is the best, because this one fall within my concentration or my machine response. So I think you understand that. You understand that? If it is, you can just type in yes, or you can.
Yeah.
Oh, good. So now let's go to some things that we have now. And again, in your calibration curve, there's something you need to look into. You need to be sure that the correlation coefficient is within the range that is required before you can accept the result, because your correlation coefficient will actually determine the validity of your result. If you've used your standard to do your calibration curve. Now, how reliable is your calibration curve? How valid it is? You need to look at the correlation coefficient. This is a formula that you can use to do that. Now this formula is saying S and Y. Don't forget, like I said earlier, your X is the concentration, your Y is the area, the measurement, the response from the machine. So you can use this formula to calculate your correlation, and the closer your value to 1, whether plus or minus 1, the better it is, the more reliable it is. Now, if your value is very close to 0, it's showing that there's no relationship between the variables. You can't just have a scatter point all around. You just have the scatter point, and you think you can use that to actually predict the amount of chemicals or the amount of compound you have in your reagent. So you need to be sure of that. You need to be sure of that. And this is the formula used to calculate your correlation. And you are not expected to come this formula. If any question is going to be coming, the formula is going to be provided. So, but just know, you need to know the significance of the result. How can you apply the result? Application is very important. How do you apply the result? How do you interpret whatever you get from your calibration, from your correlation coefficient? And then you remember during the study week, I talked about calibration curve. Here, I'm going to be talking about the method of least square. Now, this is another method of determining of estimating the unknown component, of determining the unknown component. Now, this method is very, very important. So, determining because in the industry, you don't really have the time to be plotting graph and so on and so forth. You want to computerize everything, and if you want to computerize your steps, your procedures, using the methods of least squares will support that. Method of least square will actually generate the equation at the end of the day. So the equation, you can easily program your equation to determine for example, if you have the standard equation for the experiment, you can, if you know the value of S, you can know the value of Y, or alternatively, if you know the value of Y, you can know the value of S. Now, the general equation is given as Y equals MS plus B. Your M is given as this, and your B is given as this. So, your Y, don't forget, is the machine response, and your S is the concentration. So, don't forget the two. So, and if you look at your M and Y, your M and B, you can determine that your M can be determined using this formula, and your B can be determined using this formula. Now, what does it mean? Now, this is say N, which is the numbers of variables, numbers of data you've used in your calibration curve. Your X, figure 1 is S values, and this is your Y values, and then this is summation of your X. And this is summation of your Y. This is summation of your Y. This is summation of your X. And then this is your S value, Y value. Multiplication of each for each data set. Then sum them together. That is where you have this. Your N is the numbers of variables. Now this is talking about having a square of X. Then this is talking about summing your S together, then the square of that. So you just need to know the difference between the two. What you have here in the denominator for your M is the same thing as what you have in your denominator for your B. And you can follow the same principle for your numerator for your B. Now I'm going to demonstrate how to do this. These are the example. We've been given this question. You have the amount of protein, you have the absorbance. The absorbance is your Y value. The amount of protein, which is the concentration, is your X value. Now the question is saying, use the method of least squares to determine the equation that represents the line of best fit. And if the absorbance for a similar sample measure under the same condition is 0.200, use the equation you've obtained from A to determine the amount of protein in the sample. Now, let's solve this question together. Now, you remember amount of protein is your S. Amount of the absorbance is your Y. And don't forget that if you want to use the line of best fit, you need this formula. Y equals MS plus B. And this is the formula you will need to determine your line of best fit. And don't forget the interpretation, like I said. You need, for example, you need X and Y. If you look at here, you need S and Y. So you need summation of X, which is summing this together, summation of S, summing all of this together. Then you need summation of Y, summing all of this together. Then you need S square, square of this, 25, 100, 15 square, 20 square, 25 square. Then I don't think we don't need Y square. There's nothing that says Y square in this place. So let's do this together. Now, don't forget we say we need SY. XY is 5 times this. 5 times 0.086. You need SY for each of them. Then summing them together, we give you this. This one is this. And this one, summation of X is this. And summation of Y is this. Then your S square, summation of S square, this is this. And then your summation of X, which is this, square of that is this. Please, if you understand, please give me a smiley face. Good. That's great. But unfortunately, people who are not here with us live cannot do that. So, next. So, you can see this is what I've done now. SY, I've done all of that. Then S square, the square of this is there. Then, if I want to find my M, this is the formula. M equals N, which is the numbers of sample, 5. 5. That's 5. M is number of sample, 5. Summation of SY is 22.1. This is summation of SY, 22.1. Then the next one is summation of X. Summation X is here, 75. Summation Y is here, that's 1.225. Then N again is N. Don't forget that you need to follow your BODMAS rule. Then times S square. Your summation, times summation of S square. This is summation of S square. Here is it. Here it is. And your summation of X, which is 75 square, which is 75 times 75. All you need to do is just to put all this in your calculator, and you have your M to be this. Okay? Your M is that. Now, you don't need to disturb yourself when you're calculating your B. It is the same table. The same table for your B. It is now summation of X square. Your S square is this one. And summing them together is 1375. This is it. Now, multiply that one by summation Y. Summation Y is this. Okay? So, which is this? Minus, you can see the minus there. Summation of X, Y. Now, don't forget that this is saying XY. This is XY. Can you see that? SY. Summation of XY. This is SY. This is SY. Then the sum is this. So this summation of SY is this, which is 20.1. Then multiply by summation X, which is 75. Summation X is 75. Now this is the same as what we have at the denominator for your M. 5 for N. Summation of X square is 1375. Then summation X is 75 times 75. Use your calculator carefully, and you get your B to be 0.0215. And that's all. That's what we need. You have your B to be this, you have your M to be this. From your Y, you have Y equals M, which is 0.0149 X, plus your B, which is this. This is the equation. Your Y, don't forget your Y is the absorbance, and your X is the amount of protein. Then you have the standard equation. This is what you need. Once you have this can be easily programmed into your computer system. You can use this from time to time to determine the amount of protein if you know the absorbance in the machine reading is given to you. But don't forget, whatever you are using it for has to be within the limit. You know, don't forget where we started. We started from here. Amount of protein. If your absorbance is above this figure, if your absorbance is like 0.7, you can't use this. You can't use the equation you are getting from here because it's not within the range. If your observant is 0.00001, it's outside the range. You can't use it. You need to use, it has to be within the range. Okay? It has to be within the range. So this is the equation that we have. And the equation now say, use this method of least square to determine. We've done that. Then the question now say, if the observant for a similar sample measured under the same condition is 0.2. No, 0.2 you can see 0.2 is within here, is within the range. So that is why we are able to use this formula to do that. So observant is 0.2, we put that there. Then we have this amount of protein is here. Then here is the formula, don't forget. Then we want to calculate the amount of protein. So by the time you rearrange your formula and so on and so forth, you have this. Then going to the next slide, then this is what you have. Then amount of protein in the sample will now be this one divided by 0.0149. So you have the amount of protein to be this. Okay? So that's how you get your amount of protein. Now, which is 12 milligram. If you try this with calibration curve, you will still get the same thing or something very close to this. So that's the beauty of using different methods to solve problems. Any question? Question? Yes or no?
No question, no. Understand that, cheers.
Good. Now, I'm not sure if you've managed to look at the past question attached to...
Not yet, no, that's what this weekend's for.
Okay, good. So it's going to make your job easy. Now, this is one of the calculations question that requires some attention. If you look at the question given here, you have soy sauce then was analyzed. This is very similar to your experiment, I think so, but your make experiment, very similar to your make experiment, where you use your absorbance to plot a calibration curve. So this is the question. The source cell was analyzed for protein using Biret methods. The solution of source cells will prepare 1 ml of soy sauce was diluted to 5 ml with distilled water. The second one with 10, and the third one 100. Now, assuming that the density of soy sauce is the same as water. Now, one of each of these dilution was made with this. Now, this is talking about the test. Now, you leave it for 30 minutes. Remember, you did this during your study week at room temperature. Then you put them in the tube, in the cuvette. Then you measure the control using water. Then your BSA standard also from 0 to, you have your BSA standard from 0 to 10 milligram per ml. So you have these readings. Sorry for this, is rough. You have this reading, and this has been changed 1 ml to 100. Then this is what you have for that. This is not there. Just forget about this. This is not. Let me see if I can cancel that because of people who's not, because of no, I'm not having everyone here. So this is not. Oh, I'm not sure if I can get this done. Okay, this is not part of the question. This is not part of the question. So let me see if I can get black. Okay, not part of the question. Not part of the question. So this is empty, nothing is there. So this is what we have, and this has been changed to 100 ml. Sorry, and this is not part of the question. Sorry. So this has been changed to 100 ml. And then this has been changed to 5 ml. Now the reason why they changed this one, this was a mistake, because if you look at this, the absorbance of this is absorbance of 0.03. This is absorbance of 0.86. You expect this one to be of sorry, let me go back to my pointer. The absorbance of this is 0.86. This one is 0.03. You expect this one to be of higher concentration than this one. This should be of higher concentration than this one. That's why it is 1 ml to 5 ml. So this is the question is correct now. Now the first thing to do is to plot the calibration curve. Now you are now asked to use appropriate results. Apply this to determine the concentration of protein in the original source in the original soy source as gram protein per 100 ml. Now let's start from first one. Now plotting this is straightforward. I believe you can do that. So we have 0 to 10 for my graph, and because I want to make things easy for myself, you can see this is this is from 0 to 0.8, is from 0 to 0. This, don't forget, be careful. This is what you need. This is what you need for your calibration curve. You need the standard for your calibration curve, not this. You need the standard for your what? For your calibration curve. So the standard has been used. The BSA standard has been used. Have been used because there are 10 of them. They have been used to have a calibration curve. This is from 0 to 10, I think. Yes. So this is that what we need, from 0 to 10. And we have the straight line because you know, remember, it passes through 0 because we have 0, 0. We have the control. So we have that. So we have the graph, and you can see not all the line passes through the lines, but I make sure that we stagger it in such a way that it's evenly distributed across along the line. No, it's not biased towards one side. You try to put the line in the middle, passing through 0. So this is what we have. Now, you remember we have 3 different dilutions. Now, out of these 3 different dilutions, which one do you think we are going to use for this calibration curve? Looking at the absorbance, which of the 3 do you think we use? Which of the 3 do you think is too stable to answer question number 2? We've done question number 1, plotting a calibration curve. The second one is using appropriate result. Apply this to determine the concentration of protein. Now, we want to determine the concentration of protein in air. So which one do you think we are going to use to determine the concentration of protein in the soy source? I'm listening. I'm waiting for a response.
Sorry, could you repeat that, Moses? I didn't hear that question.
Okay, if you look at the 3 dilutions, we have 1 ml to 100.
Yep.
We have the absorbance of 0.3.
Yep.
1 ml to 10. We have the absorbance of 0.53. And we have 1 ml to 5 ml. You have the absorbance of 0.86. Which of these 3 do you think is appropriate for this calibration curve?
One to 5 mil.
Say again?
1 to 5 mil.
1 to 5 mil. Now, if 1 to 5 mil is appropriate, what is the absorbance?
No, sorry. It's 1 to 10 mil, the middle one.
Good one. Good response. Because if you look at this one, the absorbance is outside. We can see. We can see 83. Now, don't forget, I've multiplied mine by 100 so that I can plot. So that I can plot it very easily. No, because I don't like dealing with all this 0.00. So don't forget that this is going to be 86. Now, if you look at our calibration curve, 86 is not there. Okay?
Yep.
So, yeah. So we can use that. And again, if you look at our calibration curve, although I think we have 3, but it's below the first reading. 0.03 is below the first reading. The first reading starts from 4. The control is actually 0. Okay?
Yep.
So the best one to use for this one will be the middle one, which is 0. And I look at that 0.53 absorbance, which is 53, because I've multiplied it by 100. Don't forget that, so that my reading can be easy, my work can be easy. So I trace that. So the concentration I got is 8.7. So I got 8.7 milligram per ml for the absorbance of 0.53. That is the diluted one. Now the question says, don't forget we've diluted it to 1 ml to 10. So 1 ml of soya sauce with dilution of 1 ml to 10 gives absorbance of 0.53 and protein concentration of 8.7 milligram per ml. So if 1 ml of original soya sauce undiluted will now be what? 8.5 times 10. Taking back our dilution factor. Okay?
Yep.
The dilution has been 1 to 100. This will be what? Multiplied by what?
100.
100. If it has been 1 ml to 5, this will be what?
5.
5, good. So you have that. So I have 87 milligram per mil. So therefore, the concentration of protein in the original source as gram protein per 100 mil. Now, don't forget that we have it in 87 milligram per mil. So we want to change that to 100 mil. So if you want to change it to 100 mil, you need to multiply this mil by 100. Because we have multiplied the denominator by 100, you need to multiply the numerator by 100. Because if you cancel this 100 by this 100, you'll still be having the same answer you have there. So you need to balance out your answers. So if this one take away this, you still be having the same thing. The reason for this is because the question says per 100 mil. So per 100 mil. So do you understand that?
Yep.
Good. So if you go to the next one, so you have the 100 mil down. Then when you multiply this by this, you have 8,700. 8,700. So now milligram. Don't forget. Milli is 1,000. 1,000 milligram equals 1 gram. 1,000 milligram equals 1 gram. So if you want to take away this mil, you need to divide this by 1,000. So when you divide that by 1,000, you have 8.7 gram. 8.7 gram, gram is greater than milligram because a gram is 1,000 milligram. So dividing this by 1,000, you have 8.7 gram per 100 mil, which equals to 8.7 gram protein per 100 mil. So in the original solution, in the undiluted, in the original soya sauce that we have for the experiment, we have 8.7 gram protein in 100 mil. In every 100 mil we've taken, we have 8.7 gram of protein. Don't forget that. In question number 3. Now, the question number 3 says that we should. Question 3 says that we should. Now, if 100 ml of soy sauce was dry at 105 degrees, now don't forget 100 ml. Now you can see the implication of this per 100 ml now. Now, if 100 ml of soy sauce was dry at 105 degrees Celsius for 24 hours to a constant weight, the mass of solid was 22.4 grams. Calculate the protein in soy sauce on a dry weight basis. Now, don't forget that in the question that we have 100 ml contains 8.7 gram protein. But the question is now saying 100 ml of soy sauce also contain 22.4 grams solid. Everything, carbohydrates, everything, sugar, salt, everything is 22, and even protein is 22.4 gram. Now the question says calculate a mass of protein per gram of dry matter. So the protein is 8.7. We've already done that in our question number 2. The total solid that we have there is 22.4. So all you need to do is just to divide, and you have 0.3884 gram of protein in every gram of dry matter. Understand?
Yep.
Good. In every gram of dry matter, you're going to be having in every gram you have 0.3884 gram protein. So that's the final answer, and I wish you the very best in your exam. Any question?
No, that's it. Thanks, Moses. Is that cover the main topics that are going to be within the exam?
To be honest, you have so many things in the blackboard side, so the lecture notes, and everything you've done in the practical week, all the lectures by Professor Tony, the lecture by Bukola, the lecture by myself. All those things are very relevant for the exam. And this revision is just trying to take just like a tips of an eye as batch. So lots of things are very important. So your lecture notes, the lectures during the study weeks are very, very important. Particularly your meeting with Tony, very, very important. You know, you did so many things during the study week, practical, the fish, everything very, very important. And
So sorry, just to clarify, so will the exam be on all aspects that are on Blackboard, or will it be based around the key topics that we covered here? I know we need to do more reading, but I'm just wondering whether there's going to be an expansion of what we've done today.
This is more or less like a revision, which is very important. And then the lectures during your study week, and most of the lectures are of course, they are in the Blackboard. Very important. And even this one, I took them out from the Blackboard. So it's also very important.
Right, okay, thanks.
Okay, any other question?
No, not from me, no. I don't think there's anyone else on, is it?
Do you have any question for Tony?
Not currently, no. I'll look through the material this week.
Okay.
And like I say, I aim to be down first thing on Thursday morning.
Okay, Tony will be here on Thursday also.
Okay.
Tony will also be
Thanks
here.
very much for putting that on, Moses.
No problem. So this is going to be recorded. This is recorded, and it's going to be uploaded as soon as it's ready on the Blackboard.
Okay.
Okay. All right. Thank you.
Cheers, Moses. Bye.
Bye. No question for you. Sorry? No question for you. Yeah. I heard calibration curve. Thank you. I didn't want to waste time. Yeah, this is good. Yeah. It's fine. Yeah. But I'll see if you need it. Yeah.